The nebular hypothesis and the formation of stars in dark molecular clouds is one of the most interesting stories in science. So we'll begin with the nebular hypothesis in the 18th century, and I've moved stellar classification up because we need to understand a relationship between stars' mass, luminosity, and temperature. Then we'll start with the star formation in the early universe, then we'll proceed to star formation in galaxies, and then I'll discuss the life cycle of the sun and star death together. Then we'll look at the birth environment of the sun, and then we'll look at the nebular hypothesis in religion and philosophy. So Immanuel Kant first proposed the nebular hypothesis in the 18th century, which is that clouds contract by gravity and form heavenly objects such as solar systems, planets with rings, and galaxies. And although the processes of formation of some of these objects are not exactly as he thought, modern telescopes have confirmed his basic concept of clouds contracting by gravity and forming stars, and then centrifugal force stretching out a disk around the objects. So one of the most amazing things about the universe is that dark molecular clouds with vacuous density eventually collapse and form stars, solar systems, and planets. So the black spaces in this image are the tentacles of a dark molecular cloud, which is blocking out the light from the stars behind them and possibly any protostars that are within them. So some people question whether such vacuous clouds could lead to highly organized, if you want to call it that, stars, planets, and solar systems. But it is possible from the perspective of the second law of thermodynamics, which allows complexity to come from disorder in the system because of gravitational energy. These things are like light, hundreds of light years possibly in length. And so when the clouds collapse, all that gravitational energy is lost and it's converted to heat and pressure in the relatively small protostar, which then triggers nuclear fusion, that heat and pressure. And then the rotation of the cloud stretches out the disk. So it doesn't violate the law of entropy to form the complexity from the clouds. So let's move on to stellar classification. Scientists became interested in stellar classification in the 19th century. And in 1894, Edward Pickering at Harvard hired Annie Jump Cannon, Henrietta Leavitt, and Ida Woods as human computers. They were called computers. This was obviously before computers. And their job was to calculate the positions and temperatures of stars from photographic plates that people had begun inserting in telescopes. Well, as it turned out, all three ladies became famous astronomers. And that's what happens when you're the person who's looking at the data, you discover things. And so the hero of this story is Annie Jump Cannon, shown in this picture. And she was actually stricken with scarlet fever when she was about 30 and lost her hearing. And she'd already sort of dedicated herself to astronomy, I think, but thereafter she was really dedicated. She did not socialize very much. She did not get married and had no children, which I guess left her plenty of time to look at stars. So she and Edward Pickering developed the Harvard classification scheme in which they classified stars based on their color and temperature. So this is the Hertzsprung-Russell diagram, and it was developed independently by two different astronomers in 1911, obviously Hertzsprung and Russell. And it shows the relationship between temperature and luminosity of stars, which are also related to temperature. So temperature is on the lower axis, and luminosity or brightness is on the vertical axis. And the main sequence phase of stars is this line from the upper left to the lower right, where you have the large blue stars in the upper left and the small reddish stars in the lower right. And it's a little bit counterintuitive, but these stars in the upper left, these blue stars, they only last for a few million years. And then they become red supergiants and supernova. Whereas the small stars at the bottom right, they might have lifespans of 10 billion years or tens of billions of years. Actually, they never burn out. And the sun is here. It's either a low mass or a medium sized star. And so it's in this yellow region, and it's going to last for 4.5 billion more years. And then it'll become a red giant, not a red supergiant. And then it'll enter into another phase where it'll finally become a white dwarf. So astrophysicists have developed several techniques to determine the processes in stars. One technique is to look at star clusters such as this. So this is a globular cluster with 100,000 stars or hundreds of thousands of stars, which all formed at approximately the same time. And the advantage of that is they can determine the age of the globular cluster based on the largest stars. And then they can see the status of stars at different phases in their lives based on the known age of the cluster. So that's just one technique that astronomers or astrophysicists use to evaluate stars. So let's go back to the first stars in the universe. So after the initial energy of the Big Bang decreased, there were no stars to light up the universe, and the universe became dark. And this period has been called the Dark Ages. But there was an important process occurring during this time. Dark matter was clumping toward the higher concentration regions of the universe left over from the initial quantum fluctuations. So based on the current observed structure of galaxies in the universe, scientists think that dark matter in the early universe formed these filaments, gathered along these filaments, which became gravity centers and attracted hydrogen and helium gas. So the dark matter could collapse because it didn't have any gas pressure resisting collapse. And so it could form these highly dense regions. And so the early stars would not have formed if it was not for dark matter. In stars and galaxies, the dust in the clouds radiates the energy out into space. So the clouds can collapse and lose energy and keep collapsing. But there was no dust in the early universe. So what needed to happen was that the dark matter filaments attracted the hydrogen and helium to the point that they heated up enough and became dense enough that they had this catastrophic gravitational collapse phase with ionization, and they formed the first protostars. And so they were these giant blue stars. Obviously, nobody took a picture of this, but this is a view of what they think it might have looked like. They were probably hundreds of times larger than the sun. And the reason they know they formed is that they altered the pattern of the cosmic microwave background radiation in the early universe. So they can see in the pattern that these stars formed. Then the early stars in the universe exploded and formed massive supernova, which then collapsed on themselves and formed massive black holes that became the centers of galaxies. And many of the black holes in the early universe form quasars, which are thousands of times brighter than the entire Milky Way. And the brightness is caused by the heating of the gas falling into the black hole. So black holes in these quasars and in galaxies, they attract gas, and so matter falls into them. And so the sun now, the black hole was massive at the beginning, but now at this time, the black hole is 4 million times more massive than the sun. And it has a diameter, in case you're interested, about the same as Mercury's orbit. But the black hole in our galaxy is not even a particularly large black hole. the black hole in the galaxy 180 M87 is 1,000 times more massive than our black hole. So as the gas clouds rotate around black holes, the gas clouds stretch out and form a disk and form a spiral galaxy. And over time, gas clouds concentrate in the arms of the galaxy. So you can see here, this is the whirlpool galaxy. So we're looking at it directly, but if we looked at it from the side, it would be a very flat disk. Anyway, for some reason, the gas clouds concentrate in these arms. And because that's a denser region with the gas clouds, that's where the stars form. And so when the clouds are compressed by merging with other clouds in the arms or by the pressure from supernova explosions, they begin to shrink and they form stars. And when the stars form, they light up the gas in the clouds and form these emission nebula, the pink areas. So that's the star forming regions in the whirlpool galaxy. And this is the Rosette Nebula, which is an emission nebula. And so the large stars form first in the center of the nebula, and they're lighting up the rest of the cloud. And the large stars will burn out quickly, and then they will contribute the materials to the rest of the cloud where other stars will form. So that's similar to what happened with our sun and our solar system. Large stars formed first, supernova exploded and contributed materials to the molecular clouds where our sun formed. So this is the famous Pillars of Creation, which is in the Orion Nebula in our galaxy, where thousands of stars have already formed. And you can see that the radiation from the other stars is lighting up the top part of this part of the Pillars of Creation. And then the rest of it is still a molecular cloud. And you can see a few stars forming within the cloud in the red dots. There's a really cool video online right now that kind of takes different views of the Pillars of Creation based on James Webb Space Telescope and Hubble Telescope. So that was a visible light image. And the dust in the cloud blocks the light, a visible light. But when scientists use an infrared telescope, they can see through the dust clouds. And so in this image, you can see the stars forming within the cloud. It can't see through all the clouds, but it can see through a lot of it. Whereas, remember, this was solid before. In the previous image, here's point A, point B, and then here's point A and point B in this infrared image. And there are, in case you're interested, you want to have a fun afternoon, there are innumerable online pictures of stars forming in molecular clouds. So I just included a couple. This is the Perseus molecular cloud in near infrared light. So this cloud has hundreds of stars forming within it and blowing the gases away. So scientists can evaluate these star formation processes by looking at the patterns of gases in the clouds and where the stars are forming. This is the Lupus dark molecular cloud, and you can see that there's two very large stars forming within it. And this this cloud also has a cool video associated with it if you want to go to this video, and it kind of zeroes in and gives you a bigger perspective on the larger cloud. And this is the Gould Belt, which I thought was interesting. This is a ribbon of massive stars that's 3,000 light years long. And scientists think that it formed because a dark molecular cloud intersected with a filament of dark matter, which collapsed the cloud and caused all these stars to form. They think it formed about 30 million years ago. Okay, let's move on to the life and death cycle of the sun and other stars. So the sun began in a dark molecular cloud and then became a protostar. And then there's different outcomes for different sized stars. Here's our sun, which formed after 10 million years of contraction. So initially it formed the protostar, but then the protostar kept contracting. Eventually, the center of the star became hot enough, 10 million degrees Kelvin, and which happened after 10 million years, and it formed the suns in the main sequence phase, where it's burning hydrogen in nuclear fusion, and that went on for, or is going on, but after 9 billion years, it will form a red giant, and then it will enter into this planetary nebula stage, and then go to the white dwarf stage, and I guess black dwarf. I didn't know about black dwarfs. Okay, the massive stars, they might form after a few million years, and then form red supergiants, and then different types of supernova. Then they might form black holes or neutron stars. And then the little red stars, they might initiate nuclear fusion, but they will last for tens of billions of years. Some stars never initiate nuclear fusion, and those are called brown dwarfs. Okay, so like I said before, in the Hertzsprung-Russell diagram, the vertical axis is luminosity and the horizontal axis is temperature. And this yellow line, we're not going to go through it all, tracks the phases of the formation of the sun. So during the catastrophic collapse phase, what happens is that the atoms begin to ionize. And so all the energy is lost due to ionization. And so that in that way, all the gas can contract and form the protostar, because there's not any energy resisting collapse. It's all getting eaten up by ionization. And so that's point A. And so this is the surface temperature of the sun. It began at 3,000 degrees or thereabouts. And then it gradually heated up over 10 million years to get to point E, which was the point at which the interior of the sun was 10 billion degrees or 10 million degrees Kelvin. And that's when the main sequence phase began. And so it'll stay on this main sequence phase for 9 billion years. And then these other stars have other sequences of formation. So this just, I just made this yellow line here to show the formation of the sun, but these other lines were already here. Okay, let's move on to the birth environment of the sun, which is in section 3-6, lots more information there. But scientists know that the sun was born in a large cluster of stars due to the evidence of heavy elements in the solar system, which came from nearby red supergiants and supernova. And so scientists are very interested in where the sun originated. So what they do is they can compare the spectral signature of the sun, which means the intensity of light versus wavelength. And so everything has a spectral signature. We use spectral signatures in agriculture to evaluate plants and things like that. But for the sun, they can go through every single spectral interval, and then they can plot the intensity of the spectra, and then they can know exactly which chemicals are in the star. So it's really interesting. And so that's called chemical tagging. And the old open cluster M67 used to be considered as the most likely location of the sun. However, stellar dynamics studies have indicated that the orbit of M67 is quite a bit above and below the plane of the Milky Way, whereas the sun is not. So scientists determined that the sun could not have emerged from M67 and have such a different orbit as M67. So they think the possibility was extremely low. Okay, and then this is the location of one star in M67 called M67 1194, which is very similar to the sun. This is why they thought it originated in that location. So this is the remaining, you can't really see it that well, but this is the remaining cluster of M67. It was born at the same time as the sun about 4.5 billion years ago and used to have tens of thousands of stars, but gradually these clusters dissipate out into space. The fact that this cluster is still together is an indication that it was a very dense starburst cluster. And this is why scientists think that the sun might have been born in M67, at least until the stellar dynamics studies. Stellar dynamics deals with the movement of stars relative to each other. But you can see that the pattern of the spectral signature is very similar to M67. And this is just one wavelength interval from 6702 to 6712 angstroms. So it's a very small part of the entire spectral signature. And so, for example, Liu et al. Made this statement in 2016. M67 is also found to have identical chemical composition to the sun, confirming its solar twin nature. Another problem with the concept that M67 was the origin of the sun is that if it was a starburst cluster, all the radiation and gravitational force from the other stars bouncing off each other or going back and forth in the cluster would have been would not have been conducive to widely spaced and circular orbiting planets. They would have destroyed the structure of the solar system. So if the sun was born in a starburst cluster, it must have left the starburst cluster very early before all that occurred. Okay, so that's it for the introduction to the chapter. There's a lot more information in the chapter on all these topics. Let's move on to philosophical approaches to the nebular hypothesis. So Kant was anti-religious. He didn't believe in religion or communication from God or anything. But I looked this up on AI. I already knew he believed this, but I just wanted to see what they said. Kant believed that the order and beauty observed in the cosmos were reflective of a rational and orderly universe, which he saw as evidence of a divine creator's design. So he wasn't religious, but he was a believer in God. So I knew that about Kant, but I was surprised to see, actually, I just looked this up this morning. I was surprised to see that most philosophers since then have basically agreed with him. Most philosophers in the 19th century, including deists and those from religious groups, saw belief in the nebular hypothesis as indicative of the divine design of the universe. And likewise, most philosophers in the 20th century had the same opinion. They saw the nebular hypothesis as in harmony with a belief in the divine design of the universe. On the other hand, atheists, such as Richard Dawkins, interpret the nebular hypothesis and other natural processes such as evolution as eliminating the need to invoke God as the cause of nature. And but I would say that other than atheists, and that's not a large part of the scientific community, most philosophers seem to agree with Kant that the processes of the nebular hypothesis are evidence of divine design. I might be wrong. I haven't looked at it in depth. And I was just I was actually kind of surprised to read that. Okay, let's look at religious approaches to the nebular hypothesis. So young Earth creationism, which really gained traction in the 1960s, holds the viewpoint that everything was created by God in its present form. So they reject all natural explanations, such as the nebular hypothesis and evolution. And prior to the 1960s, almost all religious people accepted natural explanations of the universe, solar system and Earth, such as the Big Bang, nebular hypothesis, and geologic processes, respectively. although they might have thought that God began the process or periodically intervened in the processes. But in the 19th century, scientists and theologians generally thought that the first verses of Genesis described a dark nebular cloud in verse 2, forming a light in verse 3, as in the nebular hypothesis. And the leading proponent of this viewpoint was Arnold Guyot, who was a famous scientist at Princeton. And leading theologians such as Charles Hodge and Augustus Hopkins Strong included this interpretation in their books on systematic theology, which were the primary textbooks in seminaries in the late 19th century. So for example, Arnold Guyot, who's National Geographic still gives the Arnold Guyot Prize every year. So he was a very famous scientist. There's a building named after him at Princeton and so on. But he wrote a book about his interpretation of Genesis 1 in 1884. And in the frontispiece, he included a drawing of a nebular cloud contracting and forming a light at the center. So although the nebular hypothesis of the 19th century was not accurate and was rejected with respect to the formation of the solar system in the 20th century, they still viewed it, in their viewpoint, it agreed with the idea of this dark chaos forming a light. It was rejected in the 20th century when scientists adopted the planetesimal hypothesis, which was that the sun or a passing star pulled the planets out of the sun. So that alignment of Guyot was sort of forgotten in the 20th century. But perhaps it's time to revisit it. So if verse 2 describes a dark molecular cloud as I described in chapter 2, or at least that's my opinion, then verse 3 obviously describes the formation of the sun, because verse 3 says, "Let there be light." But in the Theological Dictionary of the Old Testament, Ringren stated that if the darkness of verse 2 was a substance, then the proper interpretation is "let it become light." So that would mean let the dark molecular cloud become light. And verse 4 states that once God saw that the light was good, God separated the light from the darkness. And this is interesting because there is a strong indication in spectral data that the sun formed in the M67 cluster, but scientists can't figure out how the sun left this cluster. And so in my mind, not in anybody else's mind, that might indicate that God moved it out of the cluster. And then verse 5 goes on to say that the light is the light of day, and that obviously means that the light is the sun. So in my opinion, it's too bad Guyot died prior to seeing the fulfillment of his interpretation. Of course, he also died prior to the rejection of his interpretation. So I guess it's all good. All right, that's it.